Hello students, welcome to a session with time. Now in this session we are going to take up the second part of ozonolysis. In the previous session we had seen some aspects of this ozonolysis, especially the reductive ozonolysis. Now before we begin, I want you to check our YouTube channel. You can note this for especially for those who have joined only in this session. So see to it that you gain important knowledge watching these videos, interesting videos. So in this session, we're going to take up what all things we had started with in the previous session. What are the compounds that undergo ozonolysis? We had already talked about this. Now there we mentioned that for ozonolysis, we require a multiple bond between carbon and carbon. It could be a C double bond C or a C triple bond C. So alkenes or alkynes can undergo ozonolysis. What was the second question that we had asked? What are the different types of ozonolysis? There we mentioned we could have a reductive ozonolysis and an oxidative ozonolysis. We had also mentioned what reagents are used in reductive and what reagent is used in oxidative. We said that in oxidative, we use H2O2, which is an oxidizing agent. And in reductive, we commonly use zinc acetic acid, or methyl sulfide. Methyl sulfide can also be used instead of zinc for reductive ozonolysis. The third question we had asked was, how many products are expected from ozonolysis? Then we said, we happen to mention that it depends on the starting material. Whatever is the starting material, depending on that, the number of products, right, we can make a statement about that. How many products are expected from ozonolysis? We said that it could be an an open chain compound. For example, it is acyclic or a cyclic compound. So it depends on that. We also mentioned that the alkene could be symmetric or unsymmetric. An unsymmetrical alkene and a symmetrical alkene, that also will decide how many products are going to form. Here, then the next question was how to identify the starting material by looking at the products. This we had already done in the previous session. By looking at the products, we could construct the starting material. Mostly for an alkene we have done. Then how to identify whether the starting material is cyclic or acyclic. Even this we mentioned in the previous session, that if it is cyclic, we'll get only one product for one unsaturation, whether it is double bond or a triple bond. And for acyclic, it could break down into products. So even this we had taken up. How to identify whether the starting material is cyclic or acyclic. Now we are in a better position now to take up the second session. Now in this session, more into the other aspects of ozonolysis we'll look into, and we'll also do some questions based on that. So shall we begin? Yes. Now, how to compare reductive and oxidative ozonolysis? Suppose I had started with an alkyne, C triple bond C, which is going to interact with an ozone molecule. An ozone molecule can be represented like this: a positive oxygen because it is triply bonded, and a negative oxygen because it is only singly bonded. Now this minus from the oxygen can form a bond with that carbon, and that pi bond will break and form a bond with this oxygen. And this oxygen is going to get back its lone pair. So what do we get? C, now it has become a double bond. Then there is an oxygen here. Then there is a single bond oxygen, another single bond oxygen, and a single bond to carbon. Here, this is called the mole ozonide, which is not very stable. Mole ozonide is not stable. It has to stabilize and form a more stable ozonide. So this is the first thing that happens. I am starting it for an alkyne, right? A triple bond is there. Then what is going to happen? Check. This pi bond is going to break, right? And this is going to give a minus charge on this. And once that bond is gone, this carbon becomes positive. So the lone pair on this oxygen will run to the rescue of that carbon and check what happens. There is a C, now there is only a single bond. Then this has become a double bond O here. And what is that now? That is a double bond O with a positive charge because that O has given its lone pair. And then you have a minus here on this oxygen. So the carbons are basically neutral now. Now for the next step to, show, I would need this double bond O to go up. So that what I'll do is, I'll take this double bond O and put it up so that I can show the bond formation from this oxygen to that carbon there. From that oxygen to this carbon here. And the pi bond becoming a lone pair back on this oxygen. Here. Now let us see what has happened. The C with an O on top, with a C here, and this O, another O there, and the carbon, and one bond here, and there is one single bond between the carbons. So this is what we get. This is the stable ozonide. So if this part is clear, then we shall show how an alkene undergoes a similar kind of process. Right? So we initially formed a mole ozonide which is not stable. Then there is this amount of, what shall we say, stabilization taking place. And we get a stable ozonide now. Now because we had, I'll put another ink that it will become clear. Because we had a triple bond here, it became a double bond here, it became a single bond here, and it remained as a single bond here. Correct? Suppose I had only a double bond there, I would get a single bond here, I would get no bond here, and I would not have any bond here. Here. So now, if I am going to form a stable ozonide of an alkene, I would get C with an O on top there, with a C here, then this O, and there that O, but in between I will not have any, what shall we say, I will not have any bond between the carbon and carbon. But then because there was a double bond here, there were two bonds on this carbon. So I'll put two bonds on this carbon. So this is a stable ozonide coming from an alkene. This is from an alkyne. Clear? So mole ozonide can also be shown for an alkene and stable ozonide also for an alkene by doing a similar process. Clear? So this is reductive ozonolysis, means it is formation of an ozonide. We have to now go for a reductive or an oxidative part. Now if I have a methyl sulfide or a zinc usually with an acid, that is acetic acid, sometimes also water, right? We are going to have reductive ozonolysis. In this reductive ozonolysis, what is going to happen? We are going to have just two carbonyl compounds formed. So I would break this bond, and this bond, and whatever was present here, this will become one part from an alkene, this will become another part from an alkene, and the methyl sulfide will turn into, that is dimethyl sulfide will turn into dimethyl sulfoxide, DMSO, and zinc will turn into zinc oxide. So this is going to turn into what? DMSO by picking up on oxygen from there, and this will turn into what? Zinc oxide. Here. So that is how we get two carbonyl compounds from an alkene. And what about an alkyne? The single bond is still there. So for an alkyne, I'm putting it here, reductive ozonolysis will give what? C with a double bond O, C with a double bond O. So this is a single compound. Alkyne on reductive ozonolysis doesn't give two compounds, doesn't give two parts. It's a single part now. Whatever was there at the beginning, it is still there at the end. But for an alkene, there is no bond between carbon and carbon. And therefore, alkene will form two such carbonyl groups. Two such carbonyl compounds will form. So this is coming from an alkene. And this is coming from an alkyne. Alkyne ozonide, right, on reductive ozonolysis gives this. And alkene ozonide on reductive ozonolysis gives two carbonyl compounds. Here. And then we mentioned that if the alkene was part of a cyclic compound, you will have only one compound formed, not parts. Similarly, alkyne with reductive ozonolysis itself, it is giving for an open chain one compound, for closed chain also one compound. Here. So we'll see in the examples, in the questions that we have, right, how all these ideas can be put to use. I hope this is clear. In oxidative ozonolysis, what is going to happen? Whatever we got as a carbonyl compound, if it is an aldehyde, it will turn into a carboxylic acid, right? And for an alkyne, on either side, put an OH. So you get 2 moles of carboxylic acids. 2 moles of carboxylic acids will form when an alkyne ozonide, right, underwent reductive ozonolysis followed by oxidation. That becomes an oxidative ozonolysis. Here. So oxidative ozonolysis is oxidation of the products that you have got from reductive ozonolysis. To sum up, an alkyne gave a dicarbonyl compound, right, upon reductive ozonolysis. Upon oxidative ozonolysis, that dicarbonyl compound turned into 2 moles of carboxylic acids. Here. And for an alkene, you already got two carbonyl compounds, two parts that you got, and each part would undergo further oxidation. If it is aldehyde, it will turn into carboxylic acid. If it is ketone, it will remain as a ketone. Keep this in mind, and when we look at the examples, it will become even more clear. So reductive and oxidative ozonolysis are compared on this basis. So these two are for reductive ozonolysis. For oxidative ozonolysis, we are going to apply what? H2O2. And that H2O2 will oxidize whatever you got from reductive ozonolysis. For an alkyne, you get 2 moles of carboxylic acids. For an alkene, you would get an aldehyde oxidized to carboxylic acid and a ketone remaining as a ketone. I hope this is clear. So with the examples, with the questions that we have after this, we'll be able to establish all these things on a much firmer footing. Clear? Now look at this. Now we have got two types of ozonolysis. This is reductive and this is oxidative. First, what we will do, we will first make reductive ozonolysis product. and then that reductive ozonolysis product will oxidize. Clear? Now look at this. There is a hydrogen here which you have not shown. So break this bond. Put an O here, put an O there. That is how you get the reductive ozonolysis products. Breaking the double bond and on either side attaching a double bond O. So we got a double bond O here and a double bond O there. Here, this part is ketone. I'll write K. This part is aldehyde. Here, that you keep in mind. So this part, aldehyde will be carbon number 1. So 1 because of priority. So 2, 3, 4, 5, 6, 7. On the 6th carbon, 1, 2, 3, 4, 5, 6. On the 6th carbon, you have a ketonic group, that is oxo. So this becomes 6-oxo, and it is 7-carbon system, and aldehyde is there, so it is heptanal. So we got 6-oxo heptanal. Now the same compound, same starting material, you're going to do what? You're going to put an oxidation of that. So this is double bond O, this is double bond O, no doubt. You got this. This was an aldehyde we said. This aldehyde is going to turn into an acid. Here, on oxidative ozonolysis, whatever was aldehyde will turn into a carboxylic acid. Whatever was ketone will remain as a ketone. I hope this is clear. Yes, we mentioned that if an aldehyde is formed on reductive ozonolysis, it will turn into carboxylic acid when oxidative ozonolysis takes place using H2O2. Here, so first form the products of reductive ozonolysis and then decide upon oxidative ozonolysis. What does it do? An aldehyde will turn into a carboxylic acid, but a ketone will remain a ketone. Clear? So the ketone is still here. This has become a carboxylic acid. So this is 1, 2, 3, 4, 5, 6 and 7. This is 6-oxo-heptanoic acid. Oxo will remain oxo because ketone doesn't undergo oxidation. You know that aldehydes are very easily undergoing oxidation, whereas ketones are difficult to oxidize. Unless it is a drastic oxidation, ketones don't oxidize. And when they oxidize, they break down into a mixture of carboxylic acids, isn't it? So here with H2O2, there is no drastic oxidation, and whatever oxidation has happened, right, that will be aldehyde to carboxylic acid. That's all. The ketone will remain as ketone. I hope this is clear. Yes. So with this illustration, we'll move on further. Now this is reductive ozonolysis or oxidative ozonolysis. This is oxidative because you have H2O2. So what we will do, we'll break this, right? And we get what? This is an alkane. This is an alkyne. So you'll get a double bond. So the first thing that happens, I'm putting it here. So C with a C, then the C with a double bond O, then a C double bond O. We said dicarbonyl compound is formed out of an alkene. Now we get this. Now H2O2 is going to oxidize this. So this part is going to break. You have an OH here, you have an OH there. So what is this part? This part is C double bond O, OH with a carbon here. And that part is what? CH3, COOH. So these are the two parts that we get. Check which one is this. So this is matching here as well as here. But then this is only an aldehyde. No. Whenever you have a C double bond O, that will turn into carboxylic acid. So it has to be option 1. So CH3, CH, CH3, COOH. 1, 2, 3, 2 methyl propanoic acid and then ethanoic acid. Clear? Those are there in option 1. I hope this is clear. So this is oxidative ozonolysis of an alkyne, where you'll get 2 moles of carboxylic acids. Clear? Next, we'll test our knowledge on oxidative ozonolysis of 3-methyl hex 3-ene. Two products A and B are formed. A gives carbon dioxide with sodium bicarbonate, means it's a carboxylic acid, but B cannot. What are the structures of A and B? So let us put the starting material, 3-methyl hex 3-ene. Hex 3-ene, 1, 2, 3, 4, 5 and 6. On the third carbon, we have got the double bond. On the third carbon, you also have a methyl. There is a hydrogen here which you have not shown. Now we are going to show. Now break this first and put oxygens on either side. If it is a ketone, it will remain as a ketone. If it is an aldehyde, it will turn into a carboxylic acid upon oxidative ozonolysis. Now this on oxidative ozonolysis and this on oxidative ozonolysis we need to put down. So this is C, C, C and a C and a double bond O. It is a ketone, so it will remain like that. This is C, H and double bond O. That CHO will become COOH. And this is C and a C. So you got a carboxylic acid and a ketone. Here. So A gives carbon dioxide gas. So this is A. Therefore, this has to be B. Here. The structures of A and B are respectively. So this is what? Butanone, isn't it? If you number this, butan 2-1 is butanone. And this one is what? This is 1, 2 and 3. So this is propanoic acid. That propanoic acid will give carbon dioxide with sodium bicarbonate. You know that propanoic acid, CCCOOH with sodium bicarbonate, NaHCO3, would give what? H2CO3 and will form the salt. This is CCCOONA plus H2CO3, carbonic acid. It will decompose to give H2O and CO2. So that is how A gives us carbon dioxide. This is B, which is only butanol. Clear? I hope this is clear. So first we will make product of reductive ozonolysis and then check what is the product of reductive ozonolysis. If it is an aldehyde, it will turn into a carboxylic acid. If it is a ketone, it will remain as ketone. Here, we'll move on to the next question now. The product formed when a hydrocarbon X of molecular formula C6H10. C6H10 means it is an alkyne. Yes, it's an alkyne. Is it not? Reacted with sodamide is subjected to ozonolysis, followed by hydrolysis with zinc H2O2, and upon further oxidation gave two carboxylic acids, of which one is optically active. What is this hydrocarbon? There are choices. Yes, we'll do with this. Hex 1-ine we'll first try. So all these are CnH2n minus 2, correct? So start with X1-ine. 1, 2, 3, 4, 5 and then the sixth one. This is C6H10. Is reacted with sodamide and subjected to ozonolysis. So this part will break. So with sodamide, what are we going to get? We'll get only the salt there, right? So with ozonolysis, what are we going to get? Oxidative. C, 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 a C and a C. That will become OH. And that will become HCOOH. Both are carboxylic acids, but none is optically active. So this is not the one. Hex 3-ine, let us start here with 1, 2, 3. Now this will not react with sodamide. Out. 3-methyl pent 1-ine. 3-methyl. There is a hydrogen here. This part will break. You get two carboxylic acids. So C, 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 and a H and a C, and this will become COOH. And the other part is HCOOH, formic acid or ethanoic acid. Is this not chiral? This is chiral because it has got 4 different groups attached. So this is the one that is going to give us a carboxylic acid which is optically active and one which is not. What about the D bit? That also will check. Let us look at this part. 3,3-dimethyl but 1-ine. 3,3-dimethyl. This part is going to break. This will become COOH. And this carboxylic acid is also not chiral. That is also not chiral. That is also going to be HCOOH. Formic acid. And this acid has not got any chiral carbon. So this is not going to give. This is out because it is not reacting with NaNH2. And this will not give an optically active carboxylic acid. So it will give a mixture of carboxylic acids, both of which are not chiral. So only C, that is 3-methyl pent 1-ine, gives us one carboxylic acid which is optically active and the other which is not. I hope this is clear. Yes. Next, hexane 1256 tetraone is formed from a reagent X treated with ozone and acetic acid. So this is reductive ozonolysis. What is a possible IUPAC name of X? Is formed from a reagent X. Let us put the structure. 1, 2, 3, 4, 5, 6. Now something is not clear with the name. The naming is wrong. So if we can get something out of whatever is written here, it could be this. First carbon, second carbon, third, fourth, fifth, and then sixth. On the first carbon, there is a double bond O. The second carbon is also having a double bond O. The fifth carbon is having a double bond O. The sixth carbon is also having a double bond O. But sixth carbon has got a hydrogen there. First carbon has also got a hydrogen there. I think options are there in this. Yeah. Now, this is actually not tetraone. It is an aldehyde here and an aldehyde here, and the ones are at only second and the fifth carbon. So this is actually 2,5 dioxo hexane 1,2 dial. Correct? Now let us look at option 1, 1,3-hexadiene. So 1, 2, 3, 4, 5, 6. At the first carbon and the third carbon. No. What you will get? You will get a double bond O here, a double bond O, a double bond O, and a double bond O. So according to the name that he has written there, it could be hexane 1, 2, 3, 4 tetraone. So this is not correct. Look at the second one, 1,4-hexadiene. 1, 4. So you'll get a double bond O here, a double bond O. This is 5. A double bond O and a double bond O. So according to the name written there, in a similar way, we'll write this as what? Hexane 1, 2, 4, 5 tetraone. So we want 1, 2, 5, 6. Let us look at 2,4-hexadiene. 2, 4-hexadiene. You'll get a double bond O, a double bond O, a double bond O, and a double bond O. So 1, 2, 3, 4, 5, 6. So it will be hexane 2, 3, 4, 5 tetraone. Even this is not correct. Look at the last one, 1,5-hexadiene. 1, 2, 3, 4, 5. So you'll get a double bond O here, a double bond O, a double bond O, and a double bond O, which is what you want. So hexane 1 comma 2 comma 5 comma 6 tetra. Actually, this is the wrong name. The name should be what? This is the actual product. So it should be 2 comma 5 dioxo hexane 1 comma 6 dial. Kindly note, this is a wrong name, but we have written the right structure and then we have renamed it correctly. Here, so we find that option 4 gives us the right product that we want, which has wrongly been named, and we have put the structure by whatever has been mentioned, and then we have corrected the name. I hope this is clear. Yes. Now, suppose you had taken a closed ring and it is an aromatic benzene. Benzene undergoes ozonolysis. So we'll put the structure of benzene. Show the double bonds there. And also put the hydrogens 1, 2, 3, 4, 5 and 6. What do we normally do for ozonolysis? When you say ozonolysis, it means that it is reductive. Unless you mention that it is oxidative, people will take it as reductive. So if you simply mention it as ozonolysis, it means that it is reductive ozonolysis. So what are we doing in ozonolysis? We are breaking the double bond and on either side attaching double bond O. This double bond is broken. Either side put double bond O. This is also broken. This side one O, that side one O. So you got 3 parts. This is one part that you get. This is the second part. And that is the third part. So you get 3 moles of C double bond O, C double bond O with the hydrogen and hydrogen. Correct? So H, C double bond O, C double bond O and H. This is nothing but glyoxal, common name. This is ethane 1,2-dial. Ethane 1,2-dial is commonly called glyoxal. So benzene on ozonolysis gives 3 moles of glyoxal. Keep that in mind. Whether you start with this structure or this structure, it is not going to give any difference. So I'll put a double bond here, a double bond here, a double bond here. So the other calculus structure I have put, despite that, we will not get any difference, right? This bond is going to break, this bond will break, this bond will break, and it is the same product that we wrote here. So reductive ozonolysis of benzene gives 3 moles of glyoxal. Keep that in mind. Keep that in mind, and then let us move on further to a case where you are bound to get some problems. What is a xylene? Xylene is dimethylbenzene. You could have an orthoxylene, you could have a metaxylene, you could have a paraxylene. So let us start with an orthoxylene. Orthoxylene means where you have the 2 methyl groups at the first and the second carbon. So we'll put a CH3 and a CH3. Don't forget to put the hydrogens. Put also the hydrogens. And a hydrogen there. Put a double bond, put a double bond, put a double bond. And then break as we did for benzene. Oxygen, oxygen. Break this. Oxygen, oxygen. Also break this. Oxygen and oxygen. Now carefully remove the 3 parts. So this is one part. This is the second one I am enclosing. And that is the third one we have got. This and this are the same, glyoxal. So I'll get 2 moles of glyoxal, HC double bond O, C double bond O, and a hydrogen. But then we got this product which is called dimethyl glyoxal. Wherever the hydrogen is there, the methyl has come. So I'll call this as DMG, dimethyl glyoxal, and this is simply glyoxal. Now when we do ozonolysis of orthoxylene, this is orthoxylene, we not only get these two, there is another product formed. But how to explain that? Then people pointed out that there is another calculus structure that can be tried. Let us try with that. So there is a methyl. The first calculus structure that we had taken, we had not put a double bond between the two carbons holding CH3. Now I'll put also the hydrogens, hydrogen, and a hydrogen there. Again break the double bond. On either side attach O, double bond O. This side O, that side O. Also here O and O. Let us look at this. This is glyoxal. But look at this. What is this? This is only methyl glyoxal. And this also only methyl glyoxal. So you get 1 mole of glyoxal. Glyoxal is there, no doubt. But there is only 1 mole formed. But then there are 2 moles of CH3, C double bond O, and a C double bond O, and a hydrogen. So this is methyl glyoxal, that is glyoxal. So when orthoxylene has been subjected to ozonolysis, we not only get glyoxal, also get methyl glyoxal. We get dimethyl glyoxal. And then they are in what ratio? See, glyoxal here is 1 and there is 2. So this is 3. Methyl glyoxals are 2, 2 moles. Dimethyl glyoxal is 1. This is what we observe. Now, it also provides us one basic thing that we had covered in resonance, that one single structure cannot explain all the results. So this was structure number 1 that we took. It gave only glyoxal and dimethyl glyoxal as the products. But then we also found methyl glyoxal, which can be found only by using the second structure too. So unless we use all the structures, all the canonical structures, we cannot explain the results. It's what is taught to us through this. Ozonolysis of orthoxylene gives us an opportunity to revisit resonance, right? And then find that resonance is the inability of a single structure to explain all the results. This is clear? Yes. Now, I would like to take up even this there. We had mentioned only orthoxylene. You can take metaxylene and check what products can be formed using both the calculus structures, even paraxylene, and check if there is any difference. So this and this, right, I leave it to you, right, you can do, because we have already done for orthoxylene. A similar thing you can also do for metaxylene and paraxylene and find for yourself what exactly is happening. Clear? Now with that, we'll now move on to cyclohexadiene, ozonolysis of cyclohexadiene. Cyclohexadienes can be only of two kinds. A double bond here and a double bond here, which is conjugated, and then a double bond here and a double bond there, which is isolated. We cannot have a cumulated cyclohexadiene, sufficiently stable. This won't be there actually. This is not there at all. So conjugated is out. So this is what cyclohexa 1,3-diene. This is cyclohexa 1,4-diene. Simply break the double bond on either side, attach O and O. Also here, attach O and O, and then check what this is. You have a hydrogen here, which you can put and show. That is glyoxal. This part is what? This part is having a 4-carbon system, is it not? So a carbon here, a carbon there, a carbon there, and a carbon there. There is a hydrogen here also. So it is butane 1,4 diol. CHO, CH2, CH2, CHO. correct? And a glyoxal. So one glyoxal and one butane 1,4 diol. What about this? Break this in a similar way. Oxygen and oxygen, oxygen and oxygen. So you get two parts. So if it is cyclic and you have a double bond, you can get two products. If it is acyclic and you have only one double bond, still you'll get two products. Correct? So this is what this is: a CHO, a CH2, and a CHO, propane diol. Two such moles. Right? So check. This is symmetrical. Therefore, only one product you got. Two parts of one product. Two moles of one product. But here, the two products are different. One is glyoxal, the other is butane diol. Butane 1,4 diol is same as butane diol. Clear? So like this, you can start with various cyclic substances and then find for yourself what the products will be. So ozonolysis, we are simply doing what? Reductive. This an oxidative will give what? Wherever the aldehyde is there, that will turn into carboxylic acid. Glyoxal also will turn into oxalic acid. Two moles of 2COOH will get attached to each other. So that is oxalic acid. This will give you what? Propane 1,3 dioic acid here upon oxidative ozonolysis. Hope this is clear. Now, what should result from treating cyclopentine with ozone and then treated with hydrogen peroxide and dimethyl sulfoxide and sulfide and water? This is nothing but reductive ozonolysis, and this is oxidative ozonolysis. Correct? So let us check. Start with what? Start with cyclopentine rather. So start with cyclopentine. You have a triple bond. So first do a reductive ozonolysis. What do we get? In reductive ozonolysis, you get a dicarbonyl compound. Double bond O and a double bond O. How do you name this? Number this 1, 2, 3, 4 and 5. So cyclopentane 1,2 dione. Correct? This on oxidation, further oxidation, you will have an OH here and you will have an OH there. So this part will turn into what upon oxidation? A COOH, then a CH2, a CH2, a CH2 and a COOH. So how do you name this? Pentane 1,5 dioic acid. This is open chain now. Here. So where is this? This is not cyclopentane. This is pentane now. The ring has broken. Is it not? So cyclopentane 1,5, 1,2 diol is one thing. So 2 and 4 are out because it is 1,5 dioic acid for reductive. No, you will not get that. It's a dione, 1,2 dione, correct? And then it is pentane 1,5 dioic acid. So option 1. Remove that cyclo from there because the cyclic structure will break down to give two carboxylic acids on either end. So this is COOH, CH2, 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 COOH. Pentane, it is not cyclopentane. I hope this is clear. Yes. Now, look at this. This is, you simply have to, this is oxidative ozonolysis. So first make a product out of reductive ozonolysis. Attach one O, attach one O here. This is a ketone. It will remain as a ketone. There is an aldehyde, it will turn into carboxylic acid. Don't we get this? We get this, is it not? Wherever the CHO was there, that has turned into COOH. This is a ketone, it will remain as ketone. This part will break. There is a hydrogen there, there is a hydrogen there. So this becomes an aldehyde, this becomes an aldehyde, so they become carboxylic acids, correct? So A is 1. Look at B. attach a hydrogen here, attach a hydrogen there, break this, put oxygens on either side, break this, put oxygens on either side. This is aldehyde, this is aldehyde, they'll turn into carboxylic acid. Turned. These will remain as double bond or double bond. Yes, they remain. So B is also 2. What about C? Attach a hydrogen there, break this, attach a hydrogen, break this. This is an aldehyde, this is an aldehyde, this is an aldehyde. So carboxylic acid, carboxylic acid, carboxylic acid. This is also true. And break this oxygen on either side. That is what you got here. In fact, A is 1, B is 2, C is 3, D is 4. 1, 2, 3, 4. Option 2 it is. Here. So this you need to take a separate sheet and then put the structure, bigger structure for clarity, and then start putting the reductive ozonolysis product. Once you put the reductive ozonolysis product, whenever aldehyde is there, that is going to turn into carboxylic acid, the ketone will turn as ketone. Here. So with this, I hope we have sufficiently understood both type of ozonolysis, reductive or oxidative, whether cyclic or acyclic, whether alkene or alkyne, right? So with this, we have come to an end of this session, right? So the second session of oxidative and reductive ozonolysis, all put together, cyclic, acyclic, all those things we have done, right? So a knowledge of ozonolysis, right, is sufficiently there with you to tackle any question that you have, right, in the entrance exam. So this is the details of our website and the YouTube. You can make a note of it. And this ozonolysis forms part of class 11, right? And therefore, you may find this useful for JEE and NEET, because CUET is only for 12th. But then CUET, this ozonolysis, can form part of carboxylic acids also, aldehydes and ketones. And therefore, even there you'll encounter the same thing. And that is why you see to it that this is taken up as a part of also CUET. BitSat is anyhow there, and other entrance exams, right, of any type, whether it is state or center, not going to matter, right? Even for deemed universities, you will have all the basic material that is, taken up here for discussion useful. So see to it that you make the most of these sessions and make us part of your successful journey. Best wishes. Thank you.